Alright guys, welcome back. So here's the next video I guess in this little series I'm gonna do. So I found kind of an interesting problem. This is gonna be kind of difficult to explain initially, so just bear with me. So essentially what we have is so here's how it looks like. We have a climber, so let me just draw this. So we have a point here. We have basically 3 ropes. Let's call this rope 1, rope 3, and rope 2. Now we have a person that's, let's say, climbing this rope. And here's what we're given. The person here is 90 kilograms, not newtons, kilograms. And the maximum tension that the rope 3 can withstand before breaking, meaning this, is 1500 newtons. So this is just saying how much force this thing can take before the guy holding it rips apart. So actually this is actually all we're given, we're just given the weight of the climber and then the tension of this rope. We don't know anything about the rope 1 or rope 2. So then they want us to find what is the smallest angle that can become the rope. Well, so essentially we have to find what's the smallest angle theta that this can be before this guy breaks it and he falls to his death. That's basically what the book is saying before he dies. So, okay, kind of tricky, right? Yeah. So let me actually just put this in a different bracket. Okay. So how do we start? Well, we first have to find we'd have to do a free body diagram, which is basically find forces. So since this looks like too complicated to even draw it on one, sometimes what I like to do sometimes to make it easier is essentially to cut this off, if you will. What I mean is that we can separate complex systems into 2 simpler, like you can separate one huge system into 2 little systems. So here's what I mean. So first let's analyze the easiest one, which is this. So this thing is going here. So you just have the climber and then whatever. So we'll think it's the climber. So what are the forces right here? They're going up. Well, first you just have the tension. So let's do, so which is y equals 0 because there's no x. It's just y. So then so first you have the tension of the guy, which is up. Well, the tension of the rope, we'll call it T. And then minus you have the weight of this guy, just to make sure, yeah, the weight. So then you have the weight of the guy, mg, mass of gravity, equal to 0. So essentially this balances this guy and this guy out. So this is actually basically all that we have. So now let's do the free body diagram of this system. So let's draw this quick. T1. Actually, for now, let's just call him T1. So T. Okay. Well, to make it consistent, we'll start with T2. So then you have this crap. So what's going on here is a little more complicated. Not that complicated, but still, because the theta kind of throws things off. So first, let's analyze what's in the x first. So you have T3. And okay, for the record, just so people don't get confused, when I do free body diagrams, I always think of things on this side being positive and then things on this side being negative. For me, it helps, on the y, or things going in that direction and then going that direction. Essentially, this stuff, you make your own conventions. So you can say, oh, I want this foot to be positive and that side to be negative. Again, it's up to you, just so we don't get confused on this. So this convention of saying what's positive, saying that is completely arbitrary. It's whatever you want it to be. So T3 is over there. I'm going to make it positive, so that's over there. Then this side, I can't just say T1 because it's at an angle. So we have to say, okay, so if it's going this way, how would I present this with T1? So if you're from the Pythagorean theory, or even like the rules of the triangles, you know that any theta that corresponds with the parallel side, I guess. I think you call it adjacent or parallel, well I call it parallel, to the line, this will be cosine. And just so I'm not going crazy, I'm pretty sure it's cosine. Yeah, so it'd be cosine. I remember like cosine and then sine. So anyway, so then this would equal 0. Then we have an xy, who also has forces. Granted, there's no t3 because that's just x, but we do have a t1 sine theta. And then we have a downward force, which would be, you could kind of say it's a t2, I guess. Is this how they wrote it? Yeah. Is equal to 0. So now that we have, so now we have the forces. So what do we do from here? Well, first, you realize that you can basically combine. So let's focus on this first. So since you know T2 minus mg equals 0, you can rewrite it as T2 is equal to mg. So this is just saying that the tension is equal to the mass times the gravity. And this is helpful because now you can just plug this into here. So the T1 minus T1 sine theta minus T2 is equal to 0. Now that just becomes T1 sine theta is equal to mg. Again, I just moved this here and then converted it to this. And then so then we just keep writing. So then we know T1 cosine theta is equal to T3 because again T3. I just moved this over and then T3 goes by itself. Okay, so what do we do from here? Well, what we can do is, okay, that makes sense. Okay, so the book doesn't really make it clear, does it? Let me see. Wow, this thing's really, really confusing. So they don't even explain how they got. So basically, what they do is they do this. They say, okay, they subtract. They divide this, which would give you a tangent theta is equal to mg over T3. If that's correct, yes. Okay, well I understand this because the SOHCAHTOA rules of trigonometry tells you if you do sine by cosine you get tangent, and then this would cancel, so you would just have tangent theta. But as far as how they did it, unless it just divided the two numbers, that's all I can really see. That's probably what they did. They just divided this over this, and I guess that makes sense. That makes logical sense. I don't know, but again, unfortunately, I can't really explain how they thought they could just divide this. Maybe it's allowable, but I personally have never seen something like that before. But maybe when we did it a different way. But for some reason, I just cannot remember how we did it. But essentially, you just divide this two, and you get fan, and then essentially from there, it's easy because now you have everything. You have T3, which was this. Mass is just the guy, and then gravity is just 9.81 meters per second squared. So then, but then you wonder, okay, well, how do I find theta? Like, what's this tangent? What do I do here? So all you do is just well, it's kind of weird. Let me just rewrite it really quick. This is mg. Sorry, I know it's kind of small. T3. So what you do is you wanna cancel this. But how do you do it? So essentially, what you do is you're gonna multiply both sides by the inverse. tangent. Or you could write it like this, but this is more confusing. So people just do this. So what this will do is that since you're dividing from the inverse, you're just, so here and here, these cancel out. So all you have is theta. And then here, this is basically the same thing as saying as tangent inverse times mg over t3. This is the same thing as saying mg divided by t3, divide all that divided by tangent. Again, that's really confusing. People would just rather do this. And this is actually how you would see it in most physics textbooks. So from this point on, you have this, and you wonder, well, how do I calculate this, by hand? Well, you really can. This is where you would need a calculator. So at that point, I would just say calculator. And then from there, because, well, the most graphic calculators have a tangent inverse 1 function. You just do that, and then you just do this in, and then you get your answer. So that's it. Hope you guys enjoyed that, and we'll go on to the next video. I know it's kind of tricky, but hope you guys understood it.